So I want to have a conversation about what is a very interesting circuit, this sort of 5 transistor circuit that has some very interesting symmetry to it. It's a very interesting circuit because it definitely gets into a number of different places. One of which is you can talk about, I can have I1 and I2 as a differential input signal, and I out 1 and I out 2 as a differential output signal, and I might ask, what is the gain? We often think about gain as a voltage construct, but often we can get gain in a current construct. And so this is a differential amplifier, which is, we typically would talk about it as a Norton amplifier. That's one way to think about it, of how do we deal with these 2 inputs and 2 outputs. A similar approach is to say, this is maybe a 2-input case of what is often talked about as a winner-take-all circuit, originally coming from John Lazaro's sort of original concept in 1989. And how do I look at this circuit? Because I will care about questions of gain, because I'm going to be comparing 2 quantities, or in practice 3, 4, 7, some large integer quantities. And I really care about what does that gain look like so I can model these questions. And so the conversation here is going to be, well, what does that look like? And how does that look if I'm dealing with subthreshold transistors and dealing with them in that modeling. We can look at this above threshold, but let's start in the subthreshold space. Further, the gain activity, the place where I'm dealing with high gain, is going to be a place where M1, M2, M3, M4, and MB are all in saturation. Now, a winner-take-all circuit certainly has plenty of regions of operations where M3 and M4 will move into ohmic. One of them might move into the ohmic regime if I have a very strong winning situation. But again, for this sort of gain question, we're going to be saying, let me assume everything in here is in saturation. I'm going to be assuming that all the devices are the same, with the one comment that I'm going to assume that MB is basically two in parallel of M1 and M2 to kind of keep all of the math straightforward. And so in looking at that, I look at the structure, and one of the very first things I notice when I look at the circuit is I have a sense of symmetry. And I have symmetry at the V node here. And so there's so you sort of say, well, how do I analyze that? And I can take advantage of that symmetry. Now there's some interesting ways to do this with linear circuits, and I could do that in terms of doing small signal analysis. And that is a very interesting sort of parallel way to approach all of these conversations. And something that might be a really good exercise if you're working through this to kind of see these things. That being said, I'm going to try to keep this, keep this in a large signal sort of device level structure, so that way you can see all of the larger structure. And there's ways to kind of deal with common mode and differential mode when you have these cases. So the first thing is to think about in the common mode case, which is easier to understand in even in large signal, because basically what's going to happen is assume I1 and I2 are identical and everything else is matching. What you're going to naturally have is that this whole half the circuit will basically look like this half the circuit along the axis of symmetry. So basically if I just divide this one in half, which is why I said it'll be twice of everybody else, what I end up getting is sort of a core circuit underneath here, where I have the common current, which is the I1 and I2, so they're identical. I'd expect V1 and V2 is identical voltage, V is the same, and these 2 currents are the same. Not surprising how this works. That's a common output current, common voltage, and then the middle node is still the same. And then I look at this circuit. Now, one thing from a qualitative perspective, if I look at from VC to V, that is a source follower. I know the gain for a source follower will always give me a gain of kappa. And so this gives me a very interesting circuit, because if I look from here to here, well, it looks very, this feels very much like I almost shorted these 2 lines out, very typical diode kind of connection. And if I had that and I diode connected an element from here, from this to V, I would have something where that exponential slope is going to be related to sort of kappa over UT. Well, because I have the follower, I would expect kappa squared over UT. Well, if I work through the math, I can actually write down the nonlinear equations directly. One for IC, and the other 2 for I out sub c going through M1 and this half of MB over 2, assuming that those are all ratioed as I mentioned, the threshold currents will all be the same. It does make the math a little bit simpler here, and I can definitely see a source follower type of expression between V and VC. And the net effect is I get a transistor IC that is going to be kappa squared times VC. So completely what I would expect. Now obviously there's threshold voltage in here and UT, and this is how it would kind of enter. That's how it would work. Obviously if the WFRLs are different, that'll change the I threshold, but the overall properties will be the same. And so once I've kind of established the common mode, I might then ask, well, even with the nonlinear part of the system, what does it look like if I make a small differential current change in the structure? And this is where it gets interesting, is say, well, so I'm going to have these both be at some common level, but then there's some slight change or some small change that's going in the exact opposite direction around that bias. I like a lot of these structures analyzed like this because it makes sure that you never forget your biasing and you never forget where everything started from. It also means that you know that if I have a point of symmetry and things are moving together in this way, it means that the point of symmetry is going to be relatively fixed. Now, for really large signals, eventually you do see the nonlinearities and that will break. But let's start here by assuming that this is going to be starting as being something fixed. In that case, what you can start to say is, well, here's what my change in current looks like through M3, and so I can solve that. That gives me this first equation. Interestingly enough, that I know that the main thing here is going to be the change in V1. So what's the delta V1 change? And around VC, which is its bias point. Well, I know that all the rest of this, given the fixed voltage it's sitting at, that fixed voltage is going to be the V voltage that I will get. That's just going to be the common mode current. And so what I'm really seeing is that this is what my percentage change is going to be from the differential current to V1. A similar thing happens when I look at the output. The source voltage is fixed, and it's V1 that's the only thing that's changing, and so as a result there's a shift between the change in V1 and this sort of delta change from I out, and then I'm going to still get I out sub C here. The net effect is I get a power law. That the change in this is actually going to be some kappa over sigma power law. Now kappa over sigma is a big number, typically hundreds or some other kind of number. Well, that gives me, if I do just take the first order term of sort of the expansion of this, that's kappa over sigma ID over IC. So that gain is going to be directly reflected in what is that differential to common mode current level. And the net result is that the change of the output differential current over its common mode, which by the way is the bias current for this, is going to be equal to the high gain of the input currents over its common mode. And I can kind of write this out in terms of the actual terminals to show you what that high gain is going to look like. But what you see is out of this sort of core structure is that you definitely get some pretty high gain out of this. How much high gain? The gain of an open loop of a transistor. So kappa over sigma. So typically you'd be thinking in the hundreds range, depending on where you are and what process node that you're working with. But definitely you can kind of look at this as well as it gives you a nice way to kind of think about how to do the analysis. And in doing the analysis way, you also see the intuition working through the circuitry that gives you the various properties for, say, a Norton amp or for winner-take-all circuit.